All right, today we're going to be talking about trig functions and their inverses, exponential functions, and we're going to discuss whether or not they're continuous and what those limits might be. So in section 1.6, specifically trig, exponential, and inverse functions, what we want to talk about is how we can find those limits, some of the techniques for finding limits, and some of the basic identities that we're just going to accept as fact, okay? So in the box on the page, you can see 1.61 theorem. These are just things that you have to remember, okay? Because sine, cosine, and tangent are our parent trig functions. Remember that sine and cosine are periodic functions. Those are continuous everywhere, and therefore the limit is just going to be the function value. So for finding those limits, you're simply going to plug in whatever value you're given for c. So the limit as x approaches pi for the sine of x is just going to be equal to the sine of pi. Okay, that's all that's saying. Remember here that tangent has breaks at plus or minus pi over 2, and then every pi from there. So you have to just worry about where you're continuous, and so take that into consideration. We'll talk about these as we come along, but you'll see those infrequently in calc. All right, so example 1, find the limit. So what we want to do here is we want to go back to algebra 2, remember some of those factoring techniques, go back to pre-calc, remember how we found horizontal asymptotes, holes, and things of that sort, and then we want to utilize the principles from earlier in the chapter to actually evaluate the limit. So take a moment now, pause, and see if you can find a way to solve this. Okay, the first thing that you want to consider is taking a look at what's inside the parentheses. So we want to factor. And that's going to remove the issue. See, so in the denominator we cannot plug in 1. We're trying to evaluate it at 1. We cannot plug in 1. It causes our function to blow up. So what we want to do is use some algebra to eliminate that as an issue. And I know I can't be 1, but that's the amazing thing about limits. Who cares what's happening at 1? I only want to see what's happening as I approach 1. So now I can plug in 1, so a simple direct substitution. This is going to be the cosine of 2. Okay, so we're using the identity. I don't need to plug that into my calculator. I can, but that's going to suffice for the time being. Okay, and again, we just want to plug in and then leave the answer. Okay, so inverse functions. Remember when we're finding inverses, we switch the x and the y and we solve. And that's all good. But the important thing for limits is that if, in fact, you have a continuous function, then the inverse of that function is also continuous. That's all this is saying. So if I have a function and I can find its inverse, if the original function was continuous, so too is the inverse. Okay, again, general information. You're going to need to utilize this, not necessarily memorize it. So taking a look at the theorem, remember, it's saying that an exponential function is continuous, then the log function is also continuous. Keeping in mind, exponential functions and log functions are inverses. So it's just an example that reinforces the theorem we just talked about, okay? We don't need to memorize the specifics. We need to memorize generalized ideas so we can use those patterns. Okay, example number 3. Where is the function f of x equals to the inverse tangent of x plus the natural log of x over x squared minus 4 continuous? Okay, all I need to be looking at here is for a domain. And I want to remember what I need to be continuous, okay? In order to be continuous, there can't be any breaks in my graph. So if you'd like, you can plug this into your graphing calculator and see what it looks like. So that will help you. Remember, utilize your tools at home. The second thing I need to do, logically, is I need to remember what the 3 requirements are for continuity. So the first thing that you're looking at is the right-hand limit has to equal the left-hand limit. Okay, if those 2 things are true, then the limit of the function as x approaches a exists, okay? Keeping in mind that the second step here comes from your checking the one-sided limits. And then if that's true, the last thing that must be true is the limit that exists must be equal to the function value at that point. Okay, so you can't have any discontinuities of any kind. No points out of line. You should be able to draw your graph from start to finish without lifting your pen off the paper. And so now when we take a look at this, we have to look at a couple of things. The first thing we want to note, inverse tangent. If we don't remember what that one looks like, in our thinking bubble, inverse tangent is going to look like a sideways tangent curve, bottom and top out at pi over 2 and negative pi over 2. Okay, so that's what we want to be thinking. So, hey, guess what? Inverse tangent is continuous everywhere, so that's not going to pose a problem. What we want to look at here is we have some issues because if our denominator is 0, we're going to have a break in our graph. Okay, if the denominator is 0, in pre-calc and algebra 2, we talked about vertical asymptotes. And so we cannot be 0 in the denominator. So what numbers would make the bottom 0? Okay? So those are the two places we're going to have a break. Natural log exists only where x is greater than 0. So we're looking at greater than 0. This doesn't have any restrictions. So keep in mind, again, where the function is continuous, it has to be a smooth, continuous curve. We can't have any breaks in our graph, and we can't violate the original domains of any function. All right, 1.6.5, again, theorem. These are identities. Remember, the blue boxes are ideas that we're going to develop further, but for now, we're just going to accept them as is, right? We're talking about baby limits right now, and eventually we're going to develop some processes so we could actually solve that. For right now, what we want to do is we want to take a look at example 4, and we want to see if we can utilize those identities. Okay, those are identities. So pause now and take a look at any of those and see if you can do anything on your own. And the first thing, when I look at part A, the first thing I'm checking when I evaluate limits is, can I simply plug in? Can I use direct substitution? Here, the answer is no, because if I plug 0 in the denominator, blows up, world ceases to exist. So now I want to look at some other things. Can I use some algebra to simplify? And the answer is yes. Tangent is equivalent to the sine of x over the cosine of x. And now what I want to do is I want to take a look at fixing this fraction that I have. So this is really the same thing as sine x over cosine x times 1 over x. Now, if I rearrange that, I can get it to look like this. And now what I can do is I can say, oh, hey, look, this is the same thing as saying the limit as x goes to 0 of sine x over x and now, hey, look, woohoo, look what falls out. That's the identity. So if we scroll back up, the sine x over x, the limit as x approaches 0 of that function is equal to 1. This is not an identity, but I can evaluate that. 0 in here does not hurt my function. What's the cosine of 0? Cosine of 0 is equal to 1, so 1 over 1 is 1, so the limit of 1 is 1. And there's your final answer. Okay, so we're going to try now to apply all of that previous knowledge from limits and put it all together to evaluate some of these. Okay. This one looks very, very similar for B, not number, letter B. Only there's a 2 in there. And so what I want to do is I want to figure out, is there a way that I could possibly make B look like the theorem part A? And so I'm going to introduce something here. I'm not sure if you've attempted it before, but I'm going to show you. I'm going to say, you know what? What if I did this? What if I took this and I said, you know what? Let's let u equal to 2 theta. So then on top, it would say the sine of u. And that's good. So now I want to take and solve for theta. So I want to simply say theta is equal to u over 2. And so then I'm going to make this be u over 2. And if theta is 0, now let's come here for a second and just be thinking, if theta is 0, what does u have to be? If theta is 0, what does u have to be? Okay, 0. So what I'm going to really do is I'm going to change some things. And when we change things, we call it substitution. That's the exact same process that we use in Algebra 2, Algebra 1, Geometry, Pre-Calc, Honors Pre-Calc. It's all the same. So I'm going to substitute everything. So I'm going to convert all of my thetas to u's. So this is still 0. See, when I plug in 0 to theta, plug in 0, 2 times 0 is still 0. So the limit as u goes to 0, remember we're changing this, the sine of u we substituted to u over 2. And we say, well, that doesn't look any better yet. Because now I'm going to rewrite this. And I'm going to rewrite this fraction utilizing the same techniques that I used here. And it turns out that what I end up with is sine u over u times 2 over 1. And look at this, magic. Oh, be impressed. Not, just kidding. Okay, so the limit is u goes to 0 of sine u over u. We just talked about this looks exactly the same as this. The only difference is it's x instead of u. Who cares? I can call that letter anything I want, so long as this is the same as this is this. Okay, as long as those all three are the same, the identity is valid. Whether I use the letter T, U, Q, P, who cares? It's exactly the same. So this ends up being 1 times 2. So what's the answer for part B? 2. Okay, the next one's a little harder, so I'm going to scroll down, making sure I can remember. 3x over 5x. Okay. So now I want to take a look at part C. And I want to look at the limit as x approaches 0 of the sine of 3x over the sine of 5x. And when I look at this, make sure I copied it right. I did. Okay. So I want to do the same thing that I did on part B, and I want to use a substitution. So I want to look at this, and I want to say, hey, the sine of 3x and the sine of 5x, I don't know my identities, and I haven't memorized them, so I don't want to use that. But I do know that I can use substitution. So if I let u be equal to 5x, or u be equal to 3x, then I can make a substitution, and I need to make the same substitution across the board. So I can't change, I can't have 2 different variables. I have to use one substitution for both variables. So if I make sine be equal, if I make u be equal to 5x, let's try this way first. If I let u be equal to 5x, I need to find a way, and I can only multiply or divide here. I cannot add or subtract. If I let u be equal to 5x, then that makes it super easy here, right? Plug in x equals 0, then u is still going to go to 0. Okay, using this identity right here, I would simply plug in 0. So that works there. The second thing I need to do is find a way, because I have this 3x. And so I need to find a way to make 3x be equal to 5x. So I'm going to show you something. This would be really multiplying by 3/5. If I do the same thing to both sides, correct, then I can figure out a way to make 3x be equal to some multiple of u, and then I can deal with that. Okay, so that's the idea here. Now, I would not spend a ton of time on part C. There's a ton of algebra. But if you work it out, and we will do several of these together in class, so you will get lots more practice. Right now, I'm just going to show you what the answer is. And what I want you to see is it's going to be the same no matter what. And so what we want to do is we want to take this and we want to say the limit as x approaches 0 of sine x, oops, typo, sorry, of 3x over the limit as x approaches 0 the sine of 5x. Okay, so we want to use those limit properties. There's a little bit of algebra that's going to take place here, and then you're going to get the answer. So if you want to take a look at that, I'm going to pause for just a sec and do a little bit of work. Okay, so whether or not you do the substitution for u is equal to 3x and multiply by 5/3, or whether you use the u is equal to 5x and do by 3/5, either way, you're going to end up with an issue here, and here's the issue. Unfortunately for you, this is going to look uglier before it gets better. This is a star here because the idea of multiplying by this reciprocal, 1 over 1, we need that because we need the u on bottom. And it turns out that if I do a little bit more algebra, you can see here, if I put this in, this is our identity. So that's awesome because that's our identity. And so what we want to do is say, hey, look, this is the same as this. And so as u goes to 0, and it doesn't matter if it's 5/3 u or u in this case, this is our identity, u, u. And since these two are the same, what we want to do is say, hey, guess what? This is going to be equal to 1. Okay, that's equal to 1. The second thing we need to consider is this requires some more manipulation, because what I want you to see is that this is really sine u over u times 3/5. Okay, and that algebra is a little hard. So if you're confused at this point, please, 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 just know we're going to do more of these in class. We're going to use limit rules to pull this out front. So this is really 3/5 times the limit as u goes to 0 of sine u over u, which magically is equal to our identity, and we get 3/5 is our answer. You can check that on your calculator. The important thing here to understand is we're using a process called substitution. This right here, this box that I'm circling, this idea of making the problem look uglier before it looks better is extremely difficult. So please, please, we're going to do several more of these in class. Put a star on the slide. When we come into class tomorrow, I want you to ask questions about this, and I want you to make sure that your questions are answered. The idea of substitution to solve a calc problem is extremely beneficial. And sometimes we call them roundabout problems. You got to go roundabout it the rough way before you get the answer. So don't panic. We'll do lots more. Okay, on example 5, we just want to discuss the limit. It doesn't say to answer it. It doesn't say tell me what the answer is. If you can do that, great. But right now, we simply want to discuss it. So the first thing I note, what's the problem? Okay, I cannot plug 0 into my denominator. If I plug 0 into my denominator, direct substitution, it's going to blow up, the world ends. However, what I can do is look at numbers as that approaches 0. So I want to look at numbers that really, really, really close to 0. Remember, we're going to approach 0, and who cares what's happening at 0? So we're looking at numbers really, 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 really close to 0, and numbers just above 0, okay? So if I take a look at this, I go, okay, that would be the sign of a really big number. Well, signs of really big numbers, remember, I don't know what that is out there, but I do know that sine is always traveling between 1 and -1, right? It's always between 1 and -1. So if I plug in numbers really, really close to 0, this is going to be a very large number, okay? And depending on that number, I don't know what the sign is going to do. So what I want to consider is, hey, let's look at this inside function. Let's just take a look at the inside function. What does the function 1 over x do? Let's take a look at this. This is what I'm saying in words. What happens to this function as x approaches 0? What happens to 1 over x as x approaches 0? This should be a review of pre-calc, and it should also be a review from section 1.2 and 1.3, I believe. So the limit as x approaches 0 of 1 over x, this number is going to infinity, right? It goes to infinity on the right side, and it goes to negative infinity on the left side. Okay, so that's not going to do anything for us per se, but what we can say is, well, let me plug this into my graphing calculator and see what happens. So pull out your graphing calculators if you don't already and plug this in. Okay, so plugging into your graphing calculator, you should see something like this. So taking a look at your graph looks like as x goes towards infinity, you're approaching 0, which we anticipated was true. But remember that the sign value is going to oscillate between 1 and negative 1 always, right? It's a periodic function. And so when you look at that, the maximum and minimum values here, 1 and negative 1, right? Because no matter what, that's the only value that sign is going to be. And so as we approach 0, you notice that those are exactly the same, only on opposite sides. And if I change my window and I say, hey, I want to take a look at values that are closer to 0. So I want to start at 0.0001. And I want to increase them by 0.0001. I can take a better look at that, and I can see the graph isn't going to change. But now when I take a look at my table, I can start to see stuff happening on my table. So let me take a look at my table, and I'm going to go to my large screen. There it is. And as I scroll down my table, getting closer and closer, look at the values here. Okay, so I want to get closer and closer and closer to 0. So as I get, and then there's an error. What do you see happening to these numbers? They're getting closer and closer to a magical value. And notice they're the same on opposite sides of, and they're closing in on something. So right at 0, something is happening. Okay. So if I put my fingers on the graph, I can take a look at it that way. What I end up seeing is going to happen is those values are oscillating between plus and minus on my calculator, right? I mean, 0.3, negative 0.9. There's a big jump here, but then it goes down to negative 0.1. And so what we want to see happening is just some patterns. We're going to discuss this further because, again, we're just discussing. Okay, so we want to look at patterns. It doesn't say to solve, it just says discuss. Okay, here are your quick check exercises. Keep in mind there's a big red center note right here. Skip number 3, skip number 3, skip number 3. Okay, skip number 3. Again, if you can't read these are on page 125. I'm hoping that you're printing the notes so you have this in front of you as a hard copy. You're not writing it by hand, but if you are, you can go to page 125 to copy these questions down. The second thing I need to point out, the answers are on page 128. Remember, today we did a couple of examples that required a lot of algebra. So if you are struggling with those, there should be notes or questions on your notes so that when you come into class tomorrow, you can ask some thoughtful questions regarding the content. All right, good luck.